Let's say, again, somebody is preparing an unknown state, but they can prepare multiple copies of this state, and they send it to you, and you're doing a quantum state tomography procedure. So you measure sigma x, and you get the following results. So probability of getting +1 is 0.5. Probability of getting -1 eigenstate is 0.5. Then you measure sigma y, and you get that +1 eigenstate half of the time, and the -1 eigenstate the other half of the time. And then you measure sigma z, and now you get the +1 eigenstate a quarter of the time, and the -1 eigenstate 3/4 of the time. Okay, so if you got these results, where would you draw this state on the Bloch sphere? So the x and y are pretty easy. The expectation value here is going to be the weighted average of these. They're weighted by +1 and -1. So here you will get 0 in both cases. So it's going to be somewhere along the z-axis, because x is 0 and y is 0. But now is that? Okay. So -0.5 would put our state, so if this is a unit sphere, this is the z-axis, we'll put us like somewhere here. Okay. So you can see that this state is not on the surface of the sphere, so it can no longer be parametrized by something like this. But it's actually possible to get measurement results like this. And so in order to describe situations like that, we need to extend our formalism to incorporate states that, or incorporate density matrices that are more general than just the outer product of these states here. And so the terminology that we're going to employ is that any states that can be written like this as an outer product, they're called pure states. And in the Bloch sphere picture, the pure states live on the surface of the Bloch sphere. But anything that's inside the Bloch sphere is called a mixed state. And typically, people use the language Bloch ball when they're referring to mixed states that live inside it. So that's kind of the picture you should have in mind when we talk about the realistic realistic axiom or postulate. Okay, so let's start with preparations now. So postulate 1 says that a realistic preparation procedure is described by a density operator which is a positive semi-definite operator rho with trace 1 acting on the Hilbert space H. Okay, so let's go through each of these things. Okay, so what does positive semi-definite mean? What's a positive semi-definite matrix? Well, it's a matrix whose eigenvalues are all non-negative. So if we have A being an operator that acts on a discrete Hilbert space, then the expectation value of that operator for all states psi is going to be non-negative. And trace 1 just means that the trace of rho, which I can write in a basis spanning the Hilbert space, that's just equal to 1. Okay, so we can express density operators as convex combinations of pure states. So for a finite dimensional Hilbert space, the most general operator can be written like this. So rho can be written as a convex decomposition of these states, psi j, where psi j are pure states. But these don't have to be orthogonal. So these can be any states. And the numbers pj are non-negative. And they sum to 1. So what's an example of that decomposition for states that aren't orthogonal? Well, I could, for example, if I have my two-level system, I could write something like half outer product of 0, 0 plus a half plus plus. Where I'm defining the plus state the same way that I have on the block sphere there. Okay, so there's a neat trick for drawing states on the block sphere if you can decompose them into pure states. So if I just draw a projection, so a slice of the block sphere, just showing the x and z axes, then I can put the state 0 here, the state plus here, and then the point that corresponds to the density matrix for this preparation is just going to be the point right in the middle along the line joining these two states. So you can see that it's not a pure state because it's not on the surface of the sphere. Okay, so that's nice. But it turns out that these decompositions, so these things are not unique. So there's actually an infinite number of ways that you can decompose a density matrix or density operator. So if I look at this particular operator here, and I use this trick that my mixed state is just going to be some weighted average of pure states on the block sphere, I can see that I can decompose it as something that's a convex combination of those 2 points or really any points. So let's look at a concrete example. I can take this particular state here, and let me just call it x, and another state here, which will be orthogonal to x. And I'll show you how I can decompose this guy in terms of those states. Okay, so here I've just rewritten the same state in some other convex decomposition. That's just one specific example, but you can decompose it in almost any way that you like. Sorry. Okay, so the reason that's interesting is that you might, think that this density matrix represents the state half of the time being in this state and half of the time being in that state. You might think that, actually, the state is one of these things and rho is just some probabilistic mixture of these. But if I can decompose my density matrix in, an infinite number of ways, then you can't really think about what's happening underneath. You can't really give special privilege to any particular decomposition, since any of those decompositions are possible mathematically. Okay. So statistical mixtures or convex mixtures, they are different to coherent superpositions, so probabilistic mixtures. So if you consider this pure state, which is a coherent mixture of these states psi, then, I mean, obviously one way that it's different is that it's pure, while the density operator up there is mixed in general. But I can also see how they differ by constructing the density operator corresponding to this state. So I write the outer product that I get a component that looks like this mixed state, plus I get another component that has the cross terms. So it kind of seems like you've got bits that correspond to having one of these states in some probability pj, but really there's these other diagonal terms as well. So let's just look at a concrete example of what the implications of that are. And I'm just going to consider the case of the two-level system again, and I will look at where these states are orthogonal. So let's look at this. So our statistical or probabilistic mixture is going to be half 0, 0 plus half 1, 1. And we're going to compare it with the pure state. So we can see that these states are different. If we wanted to see operationally how they're different, we can think about what happens if we make a measurement of this state. So if we measured in the 0, 1 basis, then, and we repeated this measurement, then we would get outcome for the density operator, we would get outcome 0 half of the time and outcome 1 half of the time. But that would also be the case for this pure state. We would get outcome 0 half of the time and outcome 1 half of the time. So if they both give the same measurement results, how could we distinguish them?
Measure in a different basis?
Yes, we would measure in a different basis. So here, if you measured in a basis that corresponded to maybe the state psi and the orthogonal state, you would always get the outcome psi, while here, if you measured in that same basis, you would get the outcome psi half of the time and the outcome orthogonal to that half of the time. And we can kind of see it on the block sphere as well. So this state here that I've drawn, that would correspond to this maximally mixed state that's in the middle, while the state psi is this plus state. And so their projections onto the z-axis are the same, and their projections onto the y-axis are the same, but the projections onto the x-axis are different. So if you measure in the x basis, you'll be able to distinguish between those two things. Yes?
How can we even compare them? Because one is an operator, the other one is a state get.
Well, okay, so I'm being, what I'm saying is compare these two objects.
Okay.
Yeah. So if we wrote it out explicitly, we would get something that looks like that mixed state. But then we would get these cross terms. Like that. Yeah, so I was asking you to do that in your head. Okay, and so the final thing I wanted to say about density operators is that, so we've been kind of in a hand-wavy way talking about things like pure states and mixed states, but we can actually quantify the amount of mixedness in a state. And that's by computing a property called the purity. So where does this come from? Well, we know that pure states can be written as an outer product like this, which is the form that a projector takes. So a pure state is going to satisfy this property of idempotence that the density operator squared is just going to be equal to the density operator. So one thing you could do is to just compute the density operator squared and then compare all of the different terms. But that's computationally kind of annoying, especially if your density operator gets bigger and bigger and bigger. But what you can do is take advantage of the knowledge that your density operator always has to satisfy trace 1. So then if your state is pure, it's going to satisfy the property that trace rho squared is equal to 1. So if trace rho squared equals 1, then you know you have a pure state. And if you compute that this operation for an arbitrary state, you will see that the more mixed the state is, the further away from 1 it's going to be. And it's going to be bounded by some number from the bottom, which I'm going to ask you guys to guess. So you can do. So this example here is for a 2-level system, and that's the maximally mixed state, which is in the center of the Bloch sphere. So what would it be for this particular state? Sorry? 1/2? 1/2? Yep. So in this case, it would be a half, and in general, it's 1 on D, where D is the dimension of the system. So that corresponds to a maximally mixed state, which is always just proportional to the identity divided by the dimension of the system, or dimension of the Hilbert space. And you can see that has to be the case because you want the state to be trace 1. So you're going to add the D elements of the identity and then divide it by D. Okay, so that is all I wanted to say about realistic preparations in the context of statistical mixtures. But of course, on Thursday, we're going to look at these things in a broader context. Yes?
In ordinary quantum mechanics, with the state being given by using x as the variable, can we build states, mixed states of arbitrarily low series of rows?
Yeah, what is it for?
This D kind of
Yeah, it would have to go, I mean, in some strange limit, it would have to go to 1 on, I don't want to say 1 on infinity, but yeah, it would have to be arbitrarily big. I mean, so the dimension is going to be infinite, right?
Okay, so you know how to build an example of that?
I mean, okay, what the maximally mixed state would look like, it would, I don't want to, okay. Yeah, but then I don't know what happens with the normalization for that state. So there would have to be something out the front here to make it normalized. So yeah, I don't know how to write that down. Let me try and think. I mean, I mean, okay, I don't think that's going to be a physical state. So probably, yeah. So you can kind of do like arbitrary, like not maximally mixed states, but you could have states like that, which are mixed, and then the probability of preparing the state X would be weighted by this function. So I think that would be a physical state, and it would be mixed, but maximally mixed. I don't even know how to write that down. Yeah. But I mean, I think it's like a totally unphysical state. So that's probably why you can't write it down. Yes?
Like, we require that the sum of the probabilities equal 1, right?
Yeah.
So that would be physical under the postulates because that distribution isn't normalizable, the uniform distribution.
Yeah. You're saying it would be physical or unphysical?
It wouldn't be allowed by the postulates.
Yeah. So, okay, but all of the postulates that I'm saying are for like finite dimensional systems. So I don't want to make any statements about continuous and infinite dimensional systems. You can do it, but it's just like tricky, and I don't want to touch that in these lectures. Okay, so let's go back to my favorite block sphere. Okay, maybe, yeah, let's go to this. Or, no, okay, let's go to this one. So at the beginning of the lecture, I motivated, well, I didn't actually motivate the state. I just told you that that you did some sort of experiment and you got some statistics that told you that the density operator representing your preparation would correspond to this point here. So one way that you could make this preparation and get these statistics is to do the following thing. You could prepare the state 1, and then you could flip a coin, unbiased coin, and if you get outcome H, you could rotate the state by some angle, I don't know what that is, pi on 4. And if you get tails, you can rotate the state by the opposite angle in the other direction. And so you're just randomly doing that. Half the time you rotate it. Oh, I didn't go far enough. Okay. It'll be some other angle that's not pi on 4. But so you're probabilistically either rotating it in one direction or the other direction. And then the person doing state tomography, every time you do this preparation, they make a measurement. And then the statistics they would get would correspond to a point here. And so you can see that what that is this weighted average of the state that was rotated in that direction or in that direction. So what's going on here is that we have a transformation that takes a pure state, and then when you apply that transformation, what you get out is a density operator that's mixed. And so that type of thing clearly does not preserve unitarity, because unitary operations would correspond to rotations on the block sphere, and so they would maintain the purity of the state. So this is the motivation for now making a generalized theory of transformations that go beyond the idea that we just have unitary operation. So I will just give you the updated realistic postulate. So postulate 2 says that realistic transformations are prescribed by a completely positive trace preserving my grammar's wrong. Okay. By completely positive trace preserving maps. Which we denote by this curly E acting on rho. So what do I mean by these things? So a positive map is a map that takes a positive operator to a positive operator. And actually, for all of the maps that I'm going to discuss today, positivity is a sufficient condition. But more generally, we'll see later on that we require a stronger condition, which is complete positivity, which is defined as follows. So, let me just write this down. So if I start with a composite system, which we haven't talked about yet, but if I start with a composite system and I act the map, and this state is positive, and I act the map on only one of those components, and the thing that I get out at the end is positive, then that defines a completely positive map. So if that doesn't make sense right now, don't worry about it, because it'll become totally clear tomorrow when we talk about composite systems and when we look at some examples of maps that are positive but are not completely positive. And I'll give you a physical motivation for why this is important. But right now, just take it as a definition.
Wait, could you say it again?
So,
What a completely positive
yes,
map is?
it's a map that if I act it on one part of a composite system, then and if this input density operator is positive, then the final density operator will also be positive. Yeah, okay. I'm going to put these notes on the wiki as well, so it'll, yeah, if that didn't make sense, you can, it's written clearly in the notes. Okay, so let's consider the following procedure. Let's say with probability P, Pi, I will apply a transformation, a unitary transformation given by Ui. Then I can write down the effective transformation as this map. And so it's going to be a probabilistic mixture of the probability I applying the unitary operator to the density operator rho. And so I can actually rewrite this in terms of some other operators. And writing things down like that is known as the Krauss decomposition. And the operators AI are known as Krauss operators. So you'll see things like that in your homework, where you talk about applying certain maps to the two states that you're trying to distinguish. So it turns out that any map that you have can be decomposed in this decomposition, and typically when people are like in the quantum information community, when they're let's say modeling some sort of non-unitary evolution, what they would do is specify the Krauss operators for a particular map, and then you can use that to do your computations. Yes?
Sorry, what does it mean to apply UI but probability PI?
Like, you mean operationally? Like, okay, so I mean, so let's say I have someone prepares a state and sends it to me, and I can apply one of two unitary operations by, like, pressing a switch, and then I flip a coin with some sort of weighted coin, and depending on what outcome I get, then I apply one operation or the other operation.
And this epsilon of rho would be the resulting.
Yes, exactly. Yeah. So after I've applied this map, then I get an output state. The resulting state.
A rho sandwich between the A's, not a U?
Absolutely. Yes, thank you. Okay, and the Krauss operators, they satisfy the condition that A dagger A sums to the identity. And so that's the trace preserving condition. And okay, so if we look at, I mean, later we're going to see more general maps, but if we look at the maps that I motivated here in terms of probabilistic mixtures of unitaries, can you tell me whether these maps can increase the purity of a state? So they can definitely change the purity, because we know that they're not going to be, if I have a pure state, it won't keep it pure. But if I have a slightly mixed state and I apply this map, can I increase the purity?
It's the same.
It's the same?
This trace of rho, if we calculate the trace squared, is the same.
So actually, if you do calculate trace of rho squared, it won't be the same. Because you'll have some p squared there.
Same.
Yeah. So
It's just transforming to a square.
So you can convince yourself by going through the calculation. I will just give you a geometric intuition on the block sphere. So if I imagine let's say, okay, I start with this state, and I consider all possible unitary transformations of this, then I will get all of these. Well, I'll get a smaller sphere that describes all possible unitary transformations, and then any probabilistic mixture of these will necessarily lie inside this sphere. So anytime you apply a map that's a probabilistic mixture of unitaries, it's necessarily going to shrink the state and decrease the purity. But we'll see on Thursday that there are actually some maps that can increase the purity, but they're not performed like this.
Wait, so it can only decrease the purity?
The way that it's motivated here, yeah, it can only decrease, or it can keep it the same. Like if I only have one term in this decomposition, then it's just a unitary operation, and it'll keep the purity the same. Yeah. All right, so what I wanted to do now is to give you a little bit of a Mathematica demo to just build up a bit more intuition about how these maps work. So what I will do is, so in the quantum information literature, you'll sometimes hear of these maps referred to as quantum channels. So you can think of them as some sort of channel where you transfer quantum information, and it might undergo some type of noise, and perhaps the purity will go down. So one example of this could be like an optical fiber where you're sending your quantum information encoded in a photon, and maybe it like somehow interacts with the fiber and loses purity in some way. And so there's some standard quantum channels that people usually use to model these things, these types of interactions. So one of them is called the bit flip channel. So what a bit flip channel does is, with some probability, it does nothing, while with the rest of the time, it flips the bit. So it takes a 0 to a 1 and a 1 to a 0. And so we can model that by applying the sigma x operator to the state. So the Krauss operators for a bit flip channel are going to be square root of 1 minus p doing nothing, so applying the identity, or with probability p applying the sigma x operator, which flips a bit, takes a 0 to a 1 or a 1 to a 0. Then we have the phase flip channel, which probability 1 minus p, it does nothing. And with probability p, it flips the phase. So it changes the phase in front of the 1 in a coherent superposition. So we can do that by applying the sigma z operator. And there is something called the depolarizing channel, which has a lot of Krauss operators, which I don't want to write down. But the depolarizing channel with some probability p, it does nothing. And the rest of the time, it replaces your state with the completely mixed state. So now, could we please get the screen and for the demo? Thanks. I'm going to be asking you guys questions, so stay sharp. Yes?
So the probability.
Oh, hang on, we'll just wait one sec for it to come down. Yes?
Some probability it does nothing, with some probability it changes to a completely mixed state.
Yeah.
So that second one, you can't describe,
Yeah.
out unitary, right? So.
Not with, okay. Okay, fine, I'll just write down the Krauss operators for that. So, yeah, so it applies a phase flip, bit flip, and a combination of phase flip and bit flip. And that has the action of just like taking it to the identity. Yeah. Okay, so here is the bit flip panel. Let's start with an easy. Can you guys see that okay? So start off with the 0 state. So the bit flip channel with, as I increase P, it'll increase the probability that I flip a 0 to a 1. And so the effect of the whole channel is to just reduce the purity of the state. And then eventually I end up with a maximally mixed state. Okay, so what happens if instead I have a pure state that's maybe like somewhere here? What do we expect will happen to that state if I apply the bit flip channel? Who says it'll go to the center like it did before? Anyone? That's one. Okay, let's have a look. Turns out it just brings it to the x-axis. So it's not doing anything to the x component, but it's reducing the z component. So in that case, it doesn't actually take me to a completely mixed state. Yes? Yeah. Yeah, so that's just the model for the channel. You could increase it, and then it would also, increase in purity, but then it wouldn't model a physical process. So the particular process here just takes it to the not maximally mixed state, but it decoheres it in one axis. Yep.
Should there be square roots in the second lines of definitions?
Yes. Thanks. Okay, so and let's just, I'll ask your opinion on this one. Someone has to answer this though.
Just pull it into the XY plane again.
To the XY plane. Let's see. No. That seems counterintuitive because, yeah, you would think that what the bit flip is doing is flipping you on the equator. Well, it's a reflection in the equator, but it's not. Actually, you can't do arbitrary reflections. That would be, that's actually not a unitary operation because it wouldn't, if you want to reflect every point, you'd have to apply a different operation on every point in order to get it to reflect. So you have to think about it as a rotation. And so what it would do is rotate you to, well, I don't know how to draw it, or rotate you to the state. Yeah, okay, you can think of it as a pi rotation about the x-axis, which would take you like to the other side. So I will give you guys this notebook so you can play around with it yourself. But yeah, it always takes you to the x-axis.
Sorry, so
Yeah.
P varying between 0 and 1 here.
And a half.
Oh, okay.
Yeah. Okay, so that's the bit flip. So the phase flip, so rather than taking a 0 to a 1 and a 1 to a 0, it just changes a +1 to a -1 state with some probability. So I'm not going to go through the process of asking you all the questions, but what this one does is it just takes you to the projection onto the z-axis. So regardless of where your state is. So the other one always took you to the x-axis. This one always takes you to the z-axis. Okay. So what that actually has a name called dephasing. So what it's doing is it's reducing the coherence between the 0 and the 1, but it's maintaining the probabilities of 0 being in the 0 and 1 state. And then the final one was the depolarizing channel. And this one does what we intuitively thought the first one was going to do, and regardless of where you start, it just takes you to the identity. So if I change the state here, it'll always go to the identity. And so this one always just like completely reduces coherence in every single basis. Okay, and I have another one which I will show you on Thursday when we look at more general maps that can increase the purity. Okay, could we have the boards back, please? Hi, could we get the screen up, please? Thank you very much. Okay, and so now I want to get to the last postulate, which is the measurement postulate. And so far we saw that we can motivate realistic preparations as statistical mixtures of pure states and realistic transformations as statistical mixtures of unitary operations. So you can do the same thing for measurement and think about statistical mixtures of projective measurements. So the measurement postulate, when it's generalized, it looks like this. A realistic measurement procedure is represented by a POVM, which I will explain in a second. So the POVM is a collection of operators that have subscripts M, and then this index M refers to finding, backspace. Okay, refers to the measurement outcomes. That can occur in the experiment, and then the probability of finding outcome M given the preparation row is kind of like the Born rule, except now it's in terms of these POVM elements. Okay, so POVM stands for positive operator valued measure. Originally, they were developed in continuous systems, and so this name actually meant something, but for our purposes, we don't have to worry about what all of these terms mean. We can just think of a POVM as being any set of operators that satisfy the following condition. So we want them all to sum to the identity, and we want them to be positive. I think I broke the board. It doesn't come down. Okay.
It's just that one and that one. Because it looks like 3 boys. It's always one in front.
Okay, so maybe some language. So the set of operators is called the POVM. The operators themselves are called POVM elements. And sometimes people refer to this set as being a generalized measurement as opposed to a projective measurement. So if you hear that terminology, it's synonymous with just using a measurement described by a POVM. And so the POVM elements are actually not enough to specify a state update rule. So in order to talk about state update, you actually need to give a little bit more information about how the particular POVM is implemented. So there are different POVMs. There are measurements described by the same POVMs that will give you the same statistic, but could lead to a different state after you've performed the measurement. So in order to give the state update rule, we have to give a particular decomposition of the POVM. And that's done in terms of these things called measurement operators. So we can decompose a POVM as a sum over measurement operators. Sorry, a POVM element as a sum over measurement operators. Like this, where these measurement operators are, in general, not projectors. So then in terms of the state update rule, in terms of the measurement operators, the state update rule is as follows. That given outcome M, the post-measurement state is okay, so what do I mean physically by having measurements that can have the same POVM but different state update rules? So maybe like consider Stern, Gerlach. Is that a good example? Okay, yeah. So imagine you've got the Stern Gerlach device. So you send in some spin half particle, and you want to measure in the spin basis. So you could do some sort of projective measurement in terms of where the projectors are something like this. And I don't actually know how you would implement this this particular measurement, but you could imagine some sort of measurement that, given outcome up, it's going to project this the spin half system into the state up, and then you take that, the spin half system is now up, and you can do something else with it. So, and that would give you statistics corresponding to these projectors. But then you can imagine a different type of measurement where instead of projecting the particle into a particular state, you could just have a screen and like the particle just hits the screen and no longer exists, gets absorbed in some way. And so there, the statistics would be the same. You would get, statistics that correspond to these operators, but the post-measurement state is no longer going to be a spin up particle that you can do something else with. It's like gone. You'd have to describe it using something else, maybe like the vacuum state for electrons or something. So that seems like a more complicated, that it'll require a more complicated theory of measurement. So in that particular situation, you would have your POVM elements would correspond to these operators, and they would give you some kind of, they would predict the statistics, but then your measurement operators, maybe they would have to look something like this. So measurement operator up would be something that takes a spin half particle, but then, I don't know, outputs the vacuum state, or then the spin down one would be something like that. So in both cases, the post-measurement state is going to be like a state of no particles because the particle got absorbed by the screen. So in that case, you can construct your POVM elements out of those measurement operators. Here, you'll only have one term in the sum for that particular example. And then your post-measurement state would, in both cases, be something that corresponds to a state of no particles. But we'll see later on different types of measurements that also satisfy that description. Okay, so now I want to give a couple of examples, not worrying about the physics now, but just going back to our general states of zeros and ones. So, and so the example that I gave you wasn't motivated the way that we've been motivating everything else in terms of probabilistic mixtures. So I now want to go back to this picture where we get our description for the generalized measurement in terms of probabilistic mixtures of ideal projective measurements. Okay, so imagine I'm doing the following measurement. I have two different measurement devices. One of them can measure in the 0-1 basis. The other one can measure in the plus-minus basis. And I'm again going to flip a coin that tells me which measurement I'm going to implement. And this coin is a biased coin. So with probability 1/4, I'm going to measure in the 0-1 basis. And with probability 3/4, I will measure in the plus-minus basis. So by plus-minus basis, I mean the eigenstates of the sigma x operator. So I can write down the POVM elements for this. There will be 4 of them because I have 2 measurements with 2 outcomes each. And in this case, the measurement operators are pretty simple. They're just proportional to the POVMs. So it seems like a pretty contrived measurement that I'm describing, but it's actually, I changed the probabilities to make it a little bit more interesting. But if you had the probabilities equal, that corresponds to the measurement they were making in the Bell experiments. So they create a pair of entangled photons and send them to other parts of the lab, and then they have to randomly choose whether to measure in the in a basis corresponding to one polarization or a basis corresponding to the equivalent of this in polarization. And there, it's really important that these measurement bases are chosen randomly and in such a way that the measurement decisions are separated in a way that doesn't allow communication between the two different measurement setups. So if you wanted to describe that experiment in terms of generalized measurements, you would construct a set of POVM elements like this. So in the notes, I have an example where I then apply these operators and compute the state update rule, but I won't go through it here. Okay, and then a second example, which is kind of similar, but a little bit different. Actually, I don't think we're running out of time, so maybe I will. Yeah, maybe I will go through explicitly how to apply these things. So. Okay, so assume that the pre-measurement state was prepared in the zero density matrix. So then if we want to, we could compute the 4 probabilities associated with these POVM elements, but I will just do it for one of them. So the probability of getting outcome plus would just be a trace of the corresponding POVM element times the density operator. And then the overlap between these things is going to be a half, 1 on root 2. So you'll get 3/4 times a half from this, 1 on root 2 from this overlap, and 1 on root 2 from that overlap, so times a half. And you get 3/8. So given the measurement that I described, you're going to get, and that initial state, you'll get the outcome corresponding to plus 3/8 of the time. And then given this outcome, what's going to be the post-measurement state? Then we can apply the state update rule, where now we use the measurement operator acting on the initial state. And you can go through and divide it by 3/8. And when you go through that calculation, you end up with the density operator corresponding to plus, which is what you would expect. So in this case, it kind of acts like a projective measurement. But the probabilities are not described in terms of projectors, but in terms of these POVM elements. Okay, so now the second example. The second example will also consist of measuring in 2 different bases, but it's going to be a little bit different because here we knew which basis we made the measurement in. But you can imagine a situation where, let's say you just want to make one measurement in one basis, like maybe in the 0, 1 basis, but maybe there's like a train or subway like underneath your lab, and the train goes past and shakes everything, and so it somehow like shakes your measurement apparatus in a way that like slightly switches the basis that you're measuring in. Yes.
Sorry, can I just ask a question?
Yeah.
Why is it just 3 over root 4 and not square root 3 over 4?
Oh. Just because I'm bad at transcribing. I don't know whether it's just me or whether it's like when you've got these big letters right in front of your face, you somehow can't see them properly. Yeah, but good spot. Okay, so I'm imagining that I'm making, I've got my block sphere. And I want to measure in a basis corresponding to this axis, but something's shaking in the lab, and maybe my measurement basis is fluctuating between a continuum of different possible measurements. But just to make things simple, I only want to consider 2 possible fluctuations. So imagine one of the fluctuations corresponds to this perturbation that makes me measure in this axis by accident, and the other one corresponds to a measurement in this axis. So let me label these possible states. I'll call this 0 subscript plus epsilon, where epsilon is like the small perturbation. This one will be 0 subscript minus epsilon. And then here I have 1 subscript minus epsilon, which is orthogonal to that one, and 1 plus epsilon. Okay, so I can construct a set of POVM elements from this measurement, but they're going to be different now because we had 4 in that case because we knew which basis we were measuring in, so there were 4 possible outcomes. While here, we don't really know which fluctuation happened. We just know that there's either an outcome corresponding to something here or an outcome corresponding to something there. And then we have to average over those 2 possible outcomes. So the POVMs that describe this would be E0 and E1. So there's only 2 of them, but now we have 4 possible measurement operators. So let me write them down. I don't think you guys should be copying this, by the way, because it's all in the notes that I will put up on the wiki. So that's one set of measurement operators, and then the other one is like this. Okay, so can we check that if we add these 2 together? Oh, maybe it doesn't actually work. Yeah, now I'm like not convinced that that example actually works, but let's go with it and then we can check. Maybe we can construct. Okay, so the reason I'm worried is that if I, oh, no. Okay, no, it's okay. Yeah, I was imagining adding them together and then squaring it, and I was worried that that these are not orthogonal. But actually, what I want to do is square the element first. So do this times its Hermitian conjugate, which is just itself, plus this times its Hermitian conjugate, which will give me this measurement, this POVM element. So, okay, everything's okay. And now let's go, let's calculate some possible probabilities and what the state is after the measurement. Okay, so let's imagine, given preparation 1, okay, so now I'm preparing a density operator corresponding to this point in the Fock sphere, and now I make a measurement corresponding to this noisy situation. So the probability, let's see, the probability of getting outcome 0 is going to be trace of the POVM element times the input state. And so you can go through, and I didn't specify exactly what these states were, but we can just write it in terms of their projections onto the one state. So each one of these things, that's just an inner product, so it's going to be a complex number. And then I'm taking the absolute value squared of them. So it'll be some real number. And what's important is that this number is not equal to 0, because there is going to be some overlap between the state 1 and this noisy state. So if I was making a clean measurement that was just exactly in the 0-1 basis, I would expect the probability of getting outcome 0 given preparation 1 to be 0. But now, because my measurement is slightly noisy, there's some non-zero probability I get outcome 0. And then given outcome 0, what's the state after measurement? We're going to run out of room. Okay. Okay, I've just written it, so I don't have to write out each term. But here, what we can see is that we've got the input state, then the measurement operators either side, and then I'm summing over the two possible measurement operators. And then if I go through the calculation, what I get is the state after measurement is going to be a statistical mixture or probabilistic mixture of both of these states. just going to be, well, okay, let's write it out. So this is now not something like a projective measurement, because we started off with a pure state, and then after we make the measurement, then the state is updated into some mixed state, which is a statistical mixture of the two possible measurement outcomes of this noisy measurement. So then the description of our post-measurement state, like let's say if we wanted to now send it into some other experiment or something, it would have to be the density operator corresponding to this slightly mixed point here. Okay, so yeah, in these examples that I gave you, we had statistical mixtures of measurement operators, of projective measurements, but in the homework, you guys are going to be dealing with even more general measurements, which arise from coupling to some other ancillary system and then making a measurement on that entire system. So you'll have kind of more interesting measurement operators where, okay, because these ones you can see that they're equal to their own Hermitian conjugates, but the ones in the homework are going to be more general and they won't be equal to their own Hermitian conjugate. Okay, so that's all I wanted to say about realistic postulates in terms of statistical mixtures. And tomorrow what we're going to do is look at composite systems and entanglement to prepare us for continuing this discussion on Thursday. Are there any last questions? Okay, well, lunch.